My name is Abbie Martinez, and this is my Lab 1 Charge Tapes Lab Report. Introduction. So the purpose of this lab was to examine the interactions between two pieces of charged tape and then experimentally determine how much excess charge was present. We also want to find the length of the tape, the mass, the separation distance, and the magnitudes of the electric and gravitational force. Fundamental physics principle. Gravitational force is equal to the mass times the gravitational constant. Coulomb's law is equal to k times the magnitude of the charges divided by the magnitude of the position vector squared times the r hat vector. The electric field equals the charge of the particle times the net electric field at that position. Charge is the property of matter where the electric charge, E, is equal to 1.6 times 10 to the negative 19 coulombs. Brief preview of main results. The length of the tape was 0.2 meters, the mass of the tape was 0.0002 kilograms, there is an excess charge of about 4.3 times 10 to the 10 electrons, and the magnitude of the electric force is equal to the magnitude of the gravitational force, 1.96 times 10 to the negative 3 newtons. Models with descriptions. Observed model. In part 1, we examined the U-tape and found that the U-tape was attracted to both neutral objects and a negatively charged pen. The tape repelled the other positive tape, indicating that the U-tape was positively charged. In part 2, we observed the separation distance and found that the resulting separation was 1.5 centimeters. Here we have the measurements and assumptions used when making the calculations included later in our discussion. Importantly, F-elect is equal and opposite in magnitude of F grav, and F net equals 0. The tape is a point charge, and the charge is evenly distributed across the tape. Computational model. Coulomb's constant and the gravity constant are both defined in the code. Under the object section, both tapes are treated as point particles, and their separation distance is included within the vectors. F grav is also calculated using the particle mass and gravity as shown in the bottom part of the code. The magnitude of F-elect and F-grav are equal, charge is opposite. The definition segment in the middle calculates the charge of the particles for both tape A and tape B. All values are printed at the end, as seen at the bottom in green. Discussions and results. Here we calculated the magnitude of F-grav and equated it to F-elect. We used the fact that F net equals 0 and solved for the charge of the tape Q, which equals 7 times 10 to the negative 9 coulombs. We used the dimensions of the tape to calculate the number of atoms on the surface, then divided the Q by the electric charge to get an excess amount of the 4.4 times 10 to the negative 10 electrons. The GlowScript code indicates that the same calculations as previously mentioned. F-elect points upward and F-grav points down. Tape B is in blue, and the white particle is tape A. Possible sources of error. When handling the tape, some of the electrons from the charged tape transfer to the hand. This may cause less electrical interactions to occur and causing the tape to be neutralized. So the separation distance will be less accurate than would have happened if the charges were still an equal magnitude or existing. This is discussed more in the Y section of the conclusions. What if charges were switched? The interactions of magnitudes would remain the same. The signs of the charges would be flipped, but they would still repel each other, so nothing would really change. Why? It is important to handle the charged tapes as little as possible to avoid charge transferring from the tape to your hand. This neutralizes the tape, and the experiment may fail to show interactions. Additionally, the system would be the tape A and tape B, and the surroundings would be the hand and other objects in the environment.